Chapter 17, alcohols. There's a classic example in the properties of alcohols. Let me remind you, before I get into that though, 17 has a lot of nomenclature in terms of the alcohols. You should review those sections on nomenclature on your own. If you have questions, I'm happy to answer them during office hour. So we're starting now about 17.2. In 17.2, they're looking at the properties of alcohols. And so there's a classic example that your textbook author has chosen to give. Butane and 1-propanol. These have similar molecular weights, around 60, from 58 to 62, 65, but they have very different boiling points. So the BP for these, minus 0.5 degrees Celsius for butane. You might have heard of butane lighters, for instance. Butane is not going to be nearly at the high pressure, for instance, of propane. You might have seen propane tanks. They're stored in steel cylinders, whereas butane lighters are made of plastic, and it can easily contain the pressure. The propane has a boiling point of around 12.5 degrees Celsius. And propanol is around 97.5 degrees Celsius. So why is there such a big difference? They have similar molecular weights, but there's a huge range here, almost 100 degrees Celsius difference in the boiling point. And it has to do with hydrogen bonding. So alcohols, of course, oxygen has a lone pair. That makes it a hydrogen bond acceptor, but it also has a hydrogen, which makes it a hydrogen bond donor. So you can imagine a framework where one alcohol is hydrogen bonded to the lone pair of another one, where one acts as a hydrogen bond donor. So this hydrogen bonding two-dimensional and three-dimensional network means that there's a lot more energy that is required to break all of these hydrogen bonds to get the alcohol to leave the surface of the liquid and go into the gas phase, thus accounting for a nearly 100 degree Celsius change, 98 anyway, between butane and propanol. So now I have prepared for us here a selection of compounds, alcohols, and the thiol that's related, and their pKa's. These come out of table 17.1. So let's take a quick look. First, something familiar to us, water. Water has a pKa of 15.74. By the way, all of these pKa's are with water as the solvent. As you might imagine, the solvent plays a big role in the acidity of these compounds. And so organic solvents, you can see very different pKa's. The trends tend to be the same, but there are some important and critical places where things change order. But for now, this is good data for us to understand alcohol acidity. So water to ethanol. Ethanol, common organic solvent today, You might find it in a hand sanitizer in a 65 to 75% solution. Might be the most common place that you're finding it. Of course, it's part of the beverage industry as well. The pKa is around 16, so going from water to ethanol, there's not a terribly large change in pKa. But if we go to T-butanol, there's a 2 pKa unit change. Now remember, pKa units are log units, so this is a 10 to the 2 difference. That's a 100-fold difference in acidity, and of course that would translate to a 100-fold difference in basicity. So T-butoxide is a much stronger base than ethoxide by 100-fold. Now, what happens if we begin to put substituents on these? Well, if we go from ethanol to trifluoroethanol, the difference being those 3 fluoro groups here, we see a decrease of 3.5 pK units. Again, that's 10 to the 3.5. 10 to the third is 1,000. I'll let you get your calculators out and see what that half does to it. It's interesting, you should understand it. Because remember, pKa is a log-based function. Now, if we change oxygen to sulfur, we can compare methane thiol to ethanol. It's very close. There's a small difference between ethanol and methanol, but not enough to worry about in this comparison. And we see that this is much more acidic, and that's because the sulfur is better at stabilizing the charge. Sulfur is much larger, it's much more polarizable than oxygen, and so that large distribution of charge over space makes for a more stable situation. Of course, the more concentrated the charge is, the less stable. Now, what happens if we go from an aliphatic alcohol to an aromatic alcohol? We go from 16 to 10. Now remember, this is a 10 to the power 6 difference. That is, phenol is 1,000,000 times more acidic than ethanol. Now why is that? Could you explain that? On the basis of resonance forms, for instance. Now that we've covered aromatic groups, you should be able to, and I'm going to leave that for you as an exercise. I'm not going to cover it in lecture. And then, of course, we want to see substituent effects here, too. So if we have a paranitro group, that paranitro group makes this more acidic. And again, you should be able to draw the resonance forms to show the stabilization of that oxygen anion onto the strongly electron withdrawing nitro group. And then one final one here, this is maybe more for fun than anything else. If we make the perfluoro-T-butanol, that is, we fluorinate in all the hydrogen positions, and look at the acidity, we go from 18 to 5.4. That's a difference of 12.2. That's 10 to the 0.6 difference in acidity. Pull out your calculator and plug that one in. This is a humongous difference in acidity. So the 3 trifluoromethyl groups, and again we can explain that on the basis of polarity.